So in this video, we're going to look at the solution of the first part of the Chapter 3, Part 1 homework. So this is the first question. We have a foot valve, and the objective here is to press it in such a manner and make it rotate about point B. And ideally, it would actuate or trigger some type of pneumatic system, as is described in the problem statement. So this thing can rotate about point B. So if we apply a force down here at point A, it is going to tend to induce some rotation. The question is how much? Well, the book gives us a little bit of hint here and says, what if you think about decomposing this force into a component that's actually perpendicular to the valve itself, along with one that's parallel? And we know that if we do that decomposition, one of the advantages is the component that is parallel is going to have a line of action that goes directly through B. So it's not going to tend to induce any rotation. However, the perpendicular component is going to purely induce rotation, because we know that in order the scalar formulation of computing the moment of a force about a point, if that force is applied perpendicular to that point, we can just multiply the magnitude of the force times that perpendicular distance. So let's see how we actually go about doing this. And hopefully you can see, I'm going to show you a detailed solution, but this is pretty easy because if you look at the underlying geometry, if you just drop a perpendicular here, the perpendicular component of the force is going to be related to the magnitude times the sine of that angle. Remember though, it's applied at point A, and then that perpendicular distance will just be the distance from point A to point B, which is 170 millimeters, or in SI units, 0.17 meters. So how do we go about doing it? Well, we're looking in a local geometry that's defined by one axis that's aligned along the lever itself. I'm calling that ABC, and one axis that is perpendicular. I'm calling that ABC perpendicular. We know that the force F is applied at an angle of declination of alpha relative to this actual axis, ABC. So that is the angle that we're actually given in the problem description. But if you want to think about it in this local coordinate system, it is an angle of declination from kind of the negative ABC axis. So if we drop a perpendicular in step 2, we'll notice and kind of extend out this line of action of the applied force, as I mentioned, that dropping that perpendicular is going to be able to decompose this force into a component that's aligned along ABC and one that's perpendicular to ABC. You can find the component that is perpendicular to ABC, which is the we're calculating the moment for, by taking this magnitude and multiplying by the sine of alpha. The sine of alpha, because it is the opposite of that's the side length corresponding to the perpendicular component of the force, is opposite the angle alpha. So if you take magnitude of F times sine of alpha, that's going to give you the component that is perpendicular. And then all that we need to do now is think about what the actual distance is from the point of application of the perpendicular force. Remember, it can be generally anywhere from its line of action to the point about which we're calculating the moment. And we were given in the problem description that the distance from B to A is 170 millimeters. So that would be, in my case, may be different for you, but that would be 0.17 meters. So I know that if I have a force that's applied and I have a perpendicular distance, I can compute the moment using a scalar formulation by simply taking the value, the magnitude of this force, which is whatever the magnitude of the total force is, times sine of 28. Again, that's decomposing it into a perpendicular component, multiplied by the perpendicular distance, which is 0.17 meters. That's going to give me the magnitude of that moment. Now, the question is, what is the direction? Remember, the way you do that is you pin it at B, and you imagine yourself pulling it down and rotating the system. And hopefully you actually see that that is going in the counterclockwise direction, which corresponds to positive rotation about the z-axis. But we just, in general, when we're talking about two-dimensional moment problems, are just concerned is whether that force is rotating it in the clockwise direction or the counterclockwise direction. And in this case, it is the clockwise direction.